on your body, right? And then the x-ray tech goes behind this barrier like this and she pulls the trigger. And you're kind of getting a little nervous about, well, why is she going behind that barrier and I'm laying in front of this thing, right? Well, it's because x-rays are very, very high energy and they're actually very dangerous for us. In small doses, they're not. So if you go get an x-ray, you're going to be fine, but the lead cover kind of protects your body a little bit. But they're so high energy and so small a wavelength that they can penetrate your skin, reflect off your bones, and they can take a picture of your bones using these. But the x-ray tech has to go behind the barrier because she's taking, or he's taking, 100 of those pictures a day, and if they're constantly getting exposed to that wavelength of light, that high energy wavelength of x-rays, they would get very sick very quick and their organs would start to break down and all that type of stuff. So they have to protect themselves. And so as we're going down here, we're going less and less energy, right? And so who's ever had a sunburn before? Everybody has, right? And so that's called UV rays, right? Everybody's heard of UV rays. And we have to protect ourselves from those because they're actually very, very dangerous for us. And the beautiful part about UV rays is that as you see this picture, this UVA, UVB, UVC, the ozone protects us from a lot of these really dangerous rays. So the ozone layer that you guys have all heard about actually absorbs the most harmful rays for us. If it did not do that, right? When people talk about the ozone layer breaking down because of greenhouse gases, that's why the Earth's kind of warming up, is because it's allowing more of these really high energy, hot waves to get to our Earth's surface and starting to warm it up a little bit, right? And so we've got to really protect our ozone layer that protects our temperature of our Earth and also protects us a lot, right? And so UV rays are actually very dangerous for us, and in sort of high impact, right? If you get a lot of exposure to it, you can start to develop skin cancer, it breaks down your cells, so we can understand how dangerous that stuff is.
We just saw that a little bit when we were watching the monster. You're all right. He's gonna keep moving forward. He can maybe share this with us, but we're gonna cover this stuff as well.
Yeah.
Taking notes.
Oh, okay. Cool. And so then below UV rays is we have our visible light, right? It's all the light around us, everything that we can see. Does anybody know, when we're talking about visible light, why we see different colors? So why does that thing over there appear red? Why does this wall appear red? Why does that sign appear yellow? Does anybody know why that is?
Give it a shot.
Anybody?
Anybody? No?
Because no, not because of UV rays. Because we have this visible spectrum that contains all these colors, red, orange, yellow, green, blue, indigo, violet, and then mixtures of that. And so what the red wall is doing is it's reflecting the red wavelengths of light back to you and it's absorbing all the other wavelengths. And the same thing with why leaves appear green is because they reflect the color green, but they absorb all the rest of the visible spectrum, right? So that's why we see colors. And this visible light is a small portion. And why we call it visible light is it's because it's the wavelengths of light that our eyes are responsive to. So we can't see all these other wavelengths, right? You can't see microwave rays coming out of your microwave when you're heating up your food. It's because our eyes are not responsive to it. So our eyes are only responsive to this little narrow portion of the electromagnetic spectrum called visible light, but it's what allows our Earth to be so vibrant, us to see great colors, why the sky is blue, why the leaves are green, right? And so this is an area in visible light where we actually don't do a lot with it, except for our everyday visuals like photography, cameras, stuff like that, what we see. Most of the lasers and other sources of light that we use are outside of the visible spectrum for a lot of reasons that we'll talk about. Next is we have this, and so we're going low energy, right? We know visible light isn't dangerous to us, correct? We would be in trouble because it's all around us. And so as we go down from gamma to X-ray to UV to visible, the wavelengths are getting longer and the energy is getting lower, right? And so they're less and less dangerous for us. And so the next wavelength of light is called infrared light. Who has heard of night vision goggles? Who's heard of thermal imagers, right? And so this is an example of that. And so I'll start, you guys can pass it around. Just go ahead and grab it. You can scan it around, look at stuff, right? And so these are wavelengths beyond the visible spectrum. They're longer than that. They're not really dangerous for us at all, and they're everywhere in our everyday society. And so most people think that thermal imagers are picking up a heat signature, right? That's what we kind of think of thermal imagers. They're actually not picking up heat. Everything that's above...
Is that your camera?
Yeah, that's donated by a company in town here. So everything that's above absolute 0 Kelvin actually emits a wavelength of light. And so that's what infrared light is comprised of. Yes, see how hot I am?
Yeah, who's the hottest in the room?
Yeah.
No, Zach, you're not the hottest. Oh, no, you're not either, Danny.
And so all the different colors on that screen, you guys have all had a chance to look at it. Is it working?
Yeah,
Okay.
it sometimes delays, but it's working.
So all the different colors represent different wavelengths of light because different temperature things emit different wavelengths of light, and this is all in what we call the infrared spectrum. And then the last one, the least dangerous, the longest wavelength, the lowest energy, are we call microwave and radio waves. So everybody's driven a car and heard XM radio or FM radio or AM radio. Everybody uses a cell phone at this point, right? Everybody's warmed up their food. These are all what we call microwave and radio waves. So they're everywhere in our world. They're bouncing around us all the time, right? In this room right here, our wireless internet, you don't think of that as light because oftentimes people think of light as just the stuff we can see. But radio waves and microwaves that are cell phones, that are Wi-Fi, that are radar systems, our FM, AM radio, Sirius XM, our DirecTV, Dish Network, all that stuff is using radio waves and microwaves to transmit that information. So what I hope you guys take out of here today is that all these different things that even though we can't see it, we hear microwave and radio waves all the time, that's part of photonics, right? And that's why it's so encompassing on everything we do in our everyday society. So the beauty is, and what's allowed all this stuff to happen is that full electromagnetic spectrum we talked about, all the way from gamma rays to radio waves and microwaves, the sun actually emits every single part of that electromagnetic spectrum. All white light sources like the sun or really bright stars, they emit all of those wavelengths, right? And that's how we sort of studied that. We learned this full spectrum of the electromagnetic spectrum is because all of our light sources are doing that. Even this light source right here is producing most of that electromagnetic spectrum. And so prior to 1980, in even the 1500s and 1600s and 1700s, right, people were able to study photonics is because we had all these different wavelengths of light from the sun. And it's pretty cool. And they did a lot of crazy things like shoot light through prisms and look at it break into all the different constituents. They studied how the sun affected different aspects of our life. And so a lot of really great research happened prior to 1980. But this really cool invention happened in about 1980, a little bit before that, called the laser. Everybody's heard of a laser, right? And so when we look at the properties of a laser, it's really important to understand why they're so important. So if I look at this, these two different light sources, right? If I look at it over there, everybody can see that? Let's try to focus this a little bit. So if I show you those two light sources, what can you tell me the difference between this beam and this beam right here?
The obvious, just tell them right.
Come on.
One's stronger. Red.
One's red, and what's the other color? White, right? So when we say white, like that light bulb or the sun, even though it looks yellow, it actually comes across as white. White means polychromatic. It means it contains all wavelengths of light, right? So it's all the different colors are in there. All the reds, all the blues of our visible spectrum, and even stuff outside of the visible spectrum. And so this is red, and that's what we call monochromatic. It's called one wavelength. It's one color of light. And that's really important for a lot of applications that we'll talk about. What's another difference that you guys see between these two? One's small, the other one's big. And if I walk way over here, what do you still see? One's still really small and one's getting bigger and bigger and bigger, right? And so that's a really important property of lasers that we call coherence. And so, in all honesty, I could shoot this a mile and you could still see that beam out there. And if I shot this a mile, just like you guys know, if you walk around with a headlamp outside, you can't see very far, can you? It's because this beam is staying what we call spatially coherent, staying as a beam for really long distances. And this is not spatially coherent, and so it's just diverging like crazy. In reality, this light source right here is probably like 20 watts. And this is probably something like 20 milliwatts. So that's in 3 orders of magnitude, 1,000 times. This has 1,000 times less light in it, right? But it appears more powerful, correct? It's because of that, all that light is staying confined in a really, really tight space. And for example, this thing's putting out something like 200 watts of light. If you took a laser and all that 200 watts was in that little small beam, it would burn a hole through that wall. right? And so the power of lasers is all that light is staying confined in a really tight spot, so we can start to do really, really cool things with it that we'll talk about. And so what is a laser? It stands for light amplification by stimulated emission of radiation. That's not that important. Pat will talk about that more when you guys go back to class. But why is it important? It's monochromatic, one color, so I'll explain some things we can do with one color. It's coherent, it stays together in a tight beam. And what that means is that we have really high intensity. That says if you look up at that light source, it will not hurt you. But if I shoot this laser pointer into your eye, even though it's 1,000 times less light, could potentially burn a hole in your retina, right? And so that's really important properties of lasers that enable a lot of really, really cool things. As we go along, if you look inside this laser, if you were to tear it apart, what would be inside there would be a little tiny laser crystal. And let's go ahead and pass these around. And so what happens is a company in town called Scientific Materials will take and grow these big boules. And actually they start like this, so let's start here. So this is actually grown. It takes about maybe 3 to 4 months to grow. It looks light. It's really, really heavy, right? So one of the most densest materials that on the earth is something like that. It's called neodymium diag. It's a laser material. That material is in every laser pointer that you guys find out there. And so what they do is they'll take that big thing and they'll bore out little laser crystals like that, and then they'll go around and they'll polish it, and we'll get something like this. These are the highest purity laser crystals in the world, are grown right here in Bozeman. And so I think that's about all. So then we get different colors of laser crystals, different sizes, and they all do different things. And so you can pass those around. You can look through them. You can do a lot of cool stuff like that. I think that's all I wanted to show there. So, what lasers really enabled for us because of that spatial coherence, and if you guys pass it around, I can take it from you. We can do a lot of really cool things. And just so we're clear,